All right, so in this section, we're going to look at integration by tables. Essentially, this is what we turn to if we can't seem to figure out how to integrate something. In the beginning of this chapter, there was a list of some basic integration formulas, and in the appendix of the text, there's a big, long list of integration formulas. Some of them we already know. A lot of them are derived by using techniques that we have learned. What we're going to do in this section is just do a few examples, learn how to kind of read that table, and fit an integral to that form. So the table organizes integrals into different basic forms that involve certain types of expressions. Like here we have expressions of a radical, where we have a sum or difference of squares inside a radical. A lot of those formulas probably would involve trig substitution, or were derived by using trigonometric substitution. We have ones that involve like some kind of quadratic expression. Those things, some of those could have been derived by using partial fraction decomposition. And then we have ones that, involve trig functions or exponential functions. So when I'm looking at an integral, the first thing I do is just try to figure out, well, what section of those tables should I be looking at? A, B, and C are always constants. U is always a function, as usual. So here we have this integral dx over x times the square root of x minus 1. Now, I think I'm going to look at integrals that involve the form square root of a plus bu. Like, I'm kind of just zeroing in on what appears there, that part of the integral. So I'm going to look at the part of the table that involves the form square root a plus bu, like a constant plus a constant times a function. So let's take a look. Here's the table. So here we have forms involving a plus bu, so I'm going to skip over that. Here we've got forms involving that quadratic. Here we go. Forms involving the square root of a plus bu. And I think what we want is this one right here. Right, we had the square root of, we had 1 over x times the square root of 1 plus x. And that kind of fits this if u is equal to x and a is equal to 1. Now, this gives you different results depending on a, and our a is positive, or no, our a is negative because we had x minus 1 in there. So I think we're looking at that result. So formula 17 looks like this. And since a is negative, it gives us this result. So for us, this will fit this form if a is equal to negative 1, u is equal to x, which means, of course, du is equal to dx. I'm going to make or just make an observation here. When you're doing this integration by tables, it is pretty much the only time it's ever useful to say let u equal x as a substitution. With our kind of usual, techniques of integration, the reason we make a substitution is to get it to look different. And if you use the substitution u equals x, it doesn't look different at all. So in this section, u equals x sometimes is useful. So we're going to make this substitution. As it turns out, this is a perfect match. There's no constant factors that we need to throw in. So now let's use it. So this will be 2 over the square root of positive 1 arctan of the square root of negative 1 plus x. So I'll just write that as x minus 1 over 1 plus a constant. And then we can clean this up. You'll notice, I guess one thing I skipped over here is that the formula does involve the constant b, but for us, b is equal to 1. So I'll just make a note of that. And we'll simplify. So this is 2 arctan of the square root of x minus 1 plus a constant. All right, let's try another. Here we just want to, find the right formula and integrate. So I'm going to look at forms that involve e to the u. And I'll note that we do seem to have, this factor of x up there. If we're looking at forms that involve e to the u, and in this case, if it fits a form like that, u would have to be that negative x squared. It's kind of convenient that we have that factor of x. That would certainly could be part of du. So I'm going to take a look at the tables. Let's see, the ones that involve e to the u. Here we go. Looking at this section. And I've got, it looks like a constant plus e to the u in the bottom, and then maybe a du up top. So I think this 84 is the one we want to pick here. So that's 1 over 1 plus e to the u du. I think that's what we have. So I think it'll fit this form if we let u equal negative x squared, in which case du is equal to negative 2x dx. So we have the x dx in this integral. We need a factor of negative 2. We need a factor of negative 2 up here, which we can do as long as we put in a negative 1/2 outside. And now this fits perfectly. This part here, that is our du, and then on the bottom we have 1 plus e to the u. Great, so now let's just apply this formula. I've got to bring that factor of negative 1/2 with us, then we have u minus, so that's negative x squared minus ln of 1 plus e to the minus x squared plus a constant. I might just clean this up a little bit. I'm going to throw the factor, this negative, through. I'll distribute that part and then put the whole thing over 2. I don't know about you, but when I am using the tables to help me integrate at the end of it, I feel like I haven't done much, like I just kind of looked up a form in a table and applied it. It's not nearly as satisfying as doing an integral, by using the techniques that we have learned thus far. For this next one, let's take a look at it. When we look at it, it might think, all right, well, I'm going to look at the table, and just look at forms that involve sines and cosines. And if you do that, I don't think you're going to find anything that fits, and in part because look at all these arguments. Even if something does involve both sine and cosine, the arguments are all the same, right? The things inside the trig functions match. You know, here I have sine u, cosine u, and I have different powers. I have u times sine u. But the thing that I just, you know, kind of sticks out to me when I look at this integral is that up top, the argument is 2x inside the sine function, and in the bottom, the argument is x. So I'm going to kind of take something that we've already learned from when we were working with trig integrals and just techniques of integration in general that involve trig functions. I'm going to rewrite this, and I'm going to try to write it so that they all have the same argument. And I'm going to do that by using the double angle formula for sine. And that looks like sine 2x equals 2 sine x cosine x. So now that we've done that, if we go back to the table, spoiler alert, I think you're still not going to find it. There's not a fraction where I have, you know, a sine times cosine up top and a constant plus cosine in the bottom form here. So if it's not in the section that involves sines and cosines, then it could be it'll be in some other section, but our u will just be either sine or cosine. And so if I think of it that way, I might just look at forms that involve a plus bu. You know, like look at what we have in the bottom here, 2 plus cosine x. I could look at forms that involve a plus bu, and then think, well, okay, then maybe up top I'll have a u and a du. You know, I've got that factor of sine, and as long as I throw in a negative, then that could be my du. So I'm going to look at the table for forms that involve a plus bu. And that's right near the beginning. And right up here, I think we've got our formula. So u du up top, and then a plus bu in the bottom. I think formula 3 will work with the right substitution. So here's that formula. And to make this work, I think we're going to let u equal cosine x, in which case du is equal to minus sine x dx. And also we need a to equal 2, and b will be equal to 1. So I'm going to yank that factor of 2 outside. And then I have to throw in a negative. And now that fits. So let's apply this formula. 1 over 1 squared times 1 times cosine x minus 2 ln absolute 2 plus 1 times cosine x plus a constant, and then we clean it up a bit. Cosine x minus 2 ln 2 plus cosine x. And that don't forget that factor of negative 2 out there. Alright, let's do one more. Some of the formulas in the tables are reduction formulas. And the reduction formulas are one that have a form like this, where they say, here's how you integrate something that looks like whatever, this thing on the left, and the result is an expression that involves another integral. And so with the hope being that that other integral is one we know how to do. All of those reduction formulas are most definitely probably derived by using integration by parts on the expression. Let's try one. Here we have the integral of x cubed times sine x. So I am going to look at forms that involve sines and cosines. And if you look at, we have a power of x times sine. So I think what we want is number 54, and that's a reduction formula. It's going to allow us to rewrite the integral we have in terms of another integral. Right, and here u is equal to x, so du is dx, and n is equal to 3. So applying this formula, I get minus x cubed cosine x plus 3 integral x squared cosine x dx. But now this integral, we're going to need to use, I think, another formula for that integral. And here we have a power of x times cosine. So I'm going to go back to that same section. A power of x times cosine. Looks like that's what we've got right here. So that's number 55. Okay, and if we apply that here, I'm just going to bring down the rest of this. We have our minus x cubed cosine x plus 3 times, now I'm going to apply that formula there for the integral in the blue box. We have now x squared sine x minus 2 integral, this will just be x sine x dx. And if we look at that integral that we're left with, I think still we're looking at something that isn't just a simple form that is obvious. So we can go back to that set the tables. And let's see, our last one here. I think this will be the last one. Number 52. Yeah, so that is not a reduction formula. This one will finish it up for us. Before I apply that, let's see, I've got that integral appearing in these brackets. I'm going to just distribute that factor of 3 first. So number 52 says the integral of u sine u du is sine u minus u cosine u plus a constant. Okay, now let's apply this last formula. And then just distribute that 6. And there's our final result. It's worth noting that, this we already had a technique to do this integral. Integration by tables can be a pretty cumbersome endeavor. And not only is it not as satisfying, but sometimes it can even be more work than what we already know how to do. We could have done this problem by using the tabular method that we learned in integration by parts, where we set up that table with u and du and dv and b and chase those down. That was in section 4.2. Near the end, we did an example like this. And I think you'll agree that the work we had to do use the tabular method was less work than hunting down the right formulas and filling everything in 3 different times.